Okay, so at this point, we will discuss yung epekto ng disturbance into the steady state error of your feedback control system. Okay, so at the start of or when we introduce the topic of control systems engineering in this course, we have said na yung ating control system is built for compensation for as to compensate for disturbances that will harm our system. Okay, so isa yan sa purpose or reasons why we build a control system. Okay, now one advantage of using your feedback, okay, is that it is resilient to disturbances. Okay, so that is kahit na even in the presence of disturbance signal, your system can still be designed to follow the input with very minimal error. Okay, now at this section, what we will try to do is we will find out paano yung epekto ng disturbance signal sa steady state error performance ng control system niyo. And we will also learn kung paano natin siya mas mami-minimize pa. Okay, anong dapat nating gawin in terms of your transfer function para sa controller at saka para sa plant. Okay, in order for your steady state error for the disturbance signal be as small as possible. Okay, so we will derive the formula for finding how to find or how to compute for your steady state error due to the disturbance. And for that we will use this configuration. Okay, so in this case we will compute the output. Okay, and we will consider that this system is linear. Okay, so kung linear ito, it means na in order to find the output, we can use yung superposition principle, in which the output is actually the sum of the individual outputs due to the individual inputs. So in this case, meron tayong dalawang inputs, DS at saka RS. So ang gagawin natin is we'll find the output CS, okay, when we set RS equal to 0. Okay, and then we will find the output CS due to RS setting DS equals 0. Tapos yung makukuha nating individual outputs are then added. Okay, so yun yung superposition. So basically, ito is the output, okay, due to RS. Okay, so pag sinet natin yung DS, simply we can find the output CS as RS as E times G1 times G2. Okay, so yun yung magiging CS natin. Okay, for RS. Now for the disturbance, okay, we will set RS to 0 and then we will have simply D times G2 as our CS. Okay. Now, we also take note that CS, okay, is R minus E. Okay, kasi we start with actually E equals the input minus the output. Yun yung definition ng error natin. So solving this for C instead, we will have R minus C. Okay, now what we will do is we will substitute this equation dito, sa equation na to, sa 6.17, so that we can have R minus E equals E G1 G2 plus D G2. Okay, and we then solve this for E. Okay, so ililipat natin ito dito. Okay, and then of course yung R ililipat natin sa kabila, and then we will divide whatever is factored out in this Okay, so what will result is this equation 6.19. Okay, so pag sinolve natin ito ng kompleto, okay, ang masosolve natin is itong equation 6.19. Okay, so please verify that. Okay, now 6.19 shows some important things about the error. Okay, Una, pinapakita rin, this shows na there are two components to your error. Kapag meron kang dalawang inputs, ang error mo also has two components. Okay? Yung one component is due to the input itself. Okay? And the other component is due to the disturbance. Okay? So, yun naman din talaga yung implication ng system natin being linear. Okay? Now, what also 6.19 shows is that the error signal, okay, the error signal can be thought of as a separate system. Pwede nating tingnan itong error signal natin as actually two systems, okay, whose output is E of S. Tapos meron siyang transfer function. Okay? Tapos ang input natin is R of S. Tapos another system, okay, na ang output natin is again E of S. Tapos ang input natin is D of S, yung disturbance signal natin. Okay. Ngayon, yung transfer function na to, okay, yung closed loop transfer function na to is basically this one. Itong factor na to. Okay. And this transfer function, yung transfer function naman in terms nung ds is yung negative G2 over 1 plus G1 G2. Okay, so pwede nating tingnan yun in that angle. Okay, later on gagamitin natin yung argument na yan. Okay. Now, this is your error signal. Okay, what we are interested on is the steady state error. Okay, so we will be able to find the steady state error by applying the final value theorem. Okay, and making sure na yung roots of G1 plus 1 plus G1 G2 is on the left half plane. Okay, so we should make sure na itong dalawang system na to, itong dalawang is actually stable. Okay, so when we are trying to test this for stability, ang titingnan natin is yung roots ng 1 plus G1 G2. Okay, so now assuming na ma-apply natin yung final value theorem in that situation, we will have the following as your steady state error. So ito yung due to error, due to the input, at ito yung due to the disturbance signal. Okay, so yun na nga, we can rewrite that steady state error in terms of this. Okay, where the input, the error due to the input is given by this formula, and the error due to the steady state error due to the disturbance signal is given by this. Okay. Now, so this is now how we find yung error due to the disturbance. Okay. So, para mas matingnan pa natin siya ng konti, let us be particular, let us be specific in terms of what your disturbance signal is. Okay. So, without sacrificing some generality sa actual practice. Okay, we can actually think, okay, or we can actually assume that your disturbance signal is actually a step. So ibig sabihin nun yung ang implication nun sa actual practice is that meron kang disturbance that is persistent. Okay? For example, kung meron kang position control system para sa isang antenna, okay, at sa isang antenna na say transmitter or receiver para sa isang satellite. Okay, so ang design kasi nun is medyo parabolic. Okay, so medyo parabolic yung design nun. Parang ganito. Okay, so ngayon, since parabolic yan, medyo malaki yung surface area na to. Okay, medyo malaki yung surface area nung nung inyong dish. Okay. Kaya madaling kung malaki kasi yung surface area niyan at kung yan ay malaki rin mismo, madaling tamaan niya ng hangin, lalo na kung malakas yung hangin doon sa lugar na pinaglalagay niya. Okay? So that is why pag nag-blow yung hangin, okay, at a particular speed, okay, it would exert a constant force doon sa antenna ninyo. Okay, so halimbawa wala pa yung hangin, so yung disturbance niyo is 0. Pero pag bigla nagkaroon ng hangin, nag-exert siya ng constant force dun sa inyong antenna system o dun sa inyong dish, okay? Then magkakaroon siya ng constant na force na nai-apply sa kanya. So which typically is being modeled by a step signal. Okay. So, yung pagiging practical ng pag-assume or pagiging specific natin with a step disturbance, okay, is not really very restrictive in terms of its analysis. Okay. So, ang gagawin natin is if we assume now DS to be your disturbance signal to be as a step input. We can substitute this dito sa 6.22. Okay, and then apply yung properties ng limit niyo to come up with 6.23. Okay? So it means na yung computation ng disturbance signal, ng error due to the disturbance, given that your disturbance signal is a step signal, okay, boils down to computing two limits. Okay, one is the limit of 1 over G2 as S approaches 0, and the other one is the limit of G1 as S approaches 0. Okay, and mind you, both are DC gains. Okay, so ito is the DC gain of G1, okay, of your plant, controller. Okay, ito is yung DC gain of your controller. Okay, bali siya, ito siya, and ito siya. Okay, tapos yung the other one, ito is the DC gain, okay, DC gain of your of the plant. Okay, now let us look at this equation closely and determine kung ano yung makakapagpababa dito. Okay, so kung gusto niyo pababain itong error due to the disturbance para wala siyang may contribute dito sa kasi ang error natin, okay, ang total steady state error natin, recall, is that it is the error due to the disturbance, due to the input, plus yung error due to the disturbance. So ang gusto natin is ito, minimal yung contribution niya sa sum na to. Okay, so gusto natin mababa ito. Now, kung mababa itong natin, okay, what we would want is that this denominator to be high. Kailangan mataas tong denominator ninyo. Okay? At para mapataas yung denominator ninyo, okay, obviously, dapat itong value nito is mataas. O kaya, yung value na to is mababa. Okay? So, ito kasi, yung first expression nyo kasi is simply limit of, or it says na it's the limit of 1 over G2 as S approaches 0. Equal din yan sa 1 over the limit of G2 as S approaches 0. So, yung limit of G2, yan yung DC gain ngayon. Okay? That would be the DC gain. Okay? So, kung yan yung DC gain, since nasa denominator siya, at again, gusto nyo mataas itong buong denominator nito, kailangan tumaas itong quantity na to. Okay? So, kung tumaas yan, kailangan mababa yung DC gain. Okay? That is why, the steady state error produced by a step disturbance can be reduced by increasing the DC gain of G1. Okay, obvious naman siya dito. Or decreasing, actually, and or dapat ito. Kung pwede nyo pagsabahin na yung isa increasing, yung isa decreasing, mas maganda. That would actually minimize the steady state error due to the disturbance. Okay, so, by increasing the gain of G1, tataas ito. So, tataas din yung denominator ninyo. And hence, bababa itong error ninyo due to the disturbance. Or, by decreasing the DC gain of G2, okay? So, pag pinababa natin yung DC gain of G2, which is ito ngayon, pag binababa nyo to, yung reciprocal niya tataas. Okay, therefore, yung contribution niya sa sum na to, tataas din. And therefore, yung entire denominator nyo would actually be higher. That would lead to a lower error due to the disturbance. Okay? So, pwede natin siyang tingnan, okay, in that case where di ba sabi ko sa inyo kanina, let us look dun sa equation 6.20 as I mean 6.19. Okay, sa 6.19 as ito, pwede nating i-treat as a separate system. Okay, tapos ito yung closed loop transfer function niya. Yan. Okay, so tingnan natin ulit siya. Okay, so we will have yung D natin, okay, o yung disturbance input natin. Tapos ito yung system natin. Okay, so this would be your system. Ayan. Let E. Okay. Tapos ang ano natin dito is let us make the let us make this yung ito negative na. Okay. So that ito gawin natin G2. Okay. Over 1 plus G1 G2. Okay. So yun yung equivalent closed loop system in terms nung having negative error as your output and your D as your input. Okay? Pero pansinin niyo to na ito yung feedback formula. Okay? Ito yung parang feedback formula natin. And it would actually come from a closed loop system na ganito yung equivalent block diagram niya. So recall na kapag ito, okay, ni-reduce nyo sa single block, ito yung magiging result. Okay? Again, take note that this is negative E. So negative E yung ginamit natin dito. Okay. That negative came about from this negative sign here. Okay. So ngayon, maipapakita natin dito na kapag we increase the if the DC gain of G1 okay is increased, okay, it would lead to a lower value of error being fed back here. Okay, so magiging mababa yung error na may feedback here. Okay, so or kung i-decrease nyo naman yung DC gain nito, okay, it would result to a smaller value ng steady state error. Okay, normally kasi sa feed pagka ang nangyayari kasi is pag mababa ito, okay, mababa yung output nyo. Okay, so kapag namamataas yung feedback niyo, okay, pag mataas yung feedback niyo, mas malaki yung may susubtract niya dito. Okay, so that is why increasing this would actually make this signal higher. Okay, para mas malaki yung may subtract niya dito, therefore yung may feed niyo dito mas mababa. That would lead to a lower value of E of S. O kaya kung ito bababaan nyo outright, yung multiplier niya, yung multiplier niya para ma-generate nyo to is basically lower, which would lead to a lower E. Okay, so that is why that is how we can decrease yung error niyo due to yung steady state error niyo due to the disturbance. Okay, so let us now look at example 6.10, okay, in which we are asked to find the component of the steady state error due to the step disturbance. Okay, so ang hahanapin lang natin is yung ED. Okay, yung steady state error due to the disturbance. Okay, so again, this is equal to negative 1 over the limit of 1 over G2 as S approaches 0, okay, plus the limit of G1 as S approaches 0. Okay, so obviously ito, this is basically 0. Okay, kasi magiging yan yung reciprocal value nito, okay, kasi i-reciprocal natin siya, no? So magiging S times S plus 25. Okay, so ngayon kung i-evaluate natin yung limit niya as S approaches 0, okay, that should be 0 times 25, so that is 0, kaya 0 ito. Okay, then the other one, okay, the other part with limit ng G1 is basically limit of 1,000. So the limit of 1,000 as S approaches 0 is simply 1,000. Okay, so that is why we will have 1 over 0 plus 1,000. So yung error ninyo due to the disturbance signal is negative 1 over 1,000 or negative 0.001. Tama. 1 over 1,000. Yan. Okay. So, take note na halimbawa, pag ito, tinaasan nyo to. Okay, gawin natin 10,000 ito. Okay. What would happen is that becomes 1 over 0 plus 10,000. So that would lead or negative 1 over 0 plus 10,000. So that would lead to 1 over 10,000, which is a lower value. Okay. So again, pag tinaasan natin yung forward o yung DC gain ng controller ninyo, that would lead to a lower error due to the disturbance. Or alternatively, pwede nyo pababain din itong DC gain nito. And one easiest way or one easier way to do that is i-adjust natin kasi yung denominator nyo kasi is walang zero. So adjusting this would actually adjust yung gain nito. Okay. So that's one. Okay. Although kasi ang mangyayari dito, since this is yung plant niyo is a type 1 system. Okay, pag in-evaluate niyo yung meron siyang integration factor. Okay, so pag in-evaluate niyo yung limit nun, okay, would actually be 0. Okay, pero take note kung wala ito ha. Kung wala ito at ito ay binabaan ninyo o tinaasan ninyo, okay, pag ito ay tinaasan ninyo, okay, what would you have is say S plus 25 over say halimbawa gawin natin 2. Okay, so pag in-evaluate niyo yung limit niyan as S approach, halimbawa lang wala tong S ha. Okay, para lang makita nyo yung epekto ng pagtaas ng DC gain. Pagbaba ng DC gain. Okay, so you would have here 25 over 2. Mas mataas ito ha. Take note, tinaasan ko to. Okay, so 25 over 2 yung DC gain niyo compared to say 1 lang talaga siya. That should lead us to the limit of S plus 25 over 1 as S approaches 0. Okay, so that should give you 25. Okay, so again, pag tinaasan nyo yung forward gain nito o yung gain nitong plant niyo, that should lead to a lower DC gain. Okay? Para dito sa factor na to. Okay? So, ayun. Now, let us try to analyze yung results na nakuha natin. Okay. So, number one. Ang nakuha nating error due to the disturbance is negative 1 over 1,000. Okay. So, kung negative siya, okay, that should imply na the output has been higher against the input. Okay. So, ibig sabihin nun, pinapataas ito yung signal mo or mas mataas yung output mo. Okay, dun sa dapat na value niya. For example, halimbawa pag nagkaroon tayo ng error na negative 1. Okay. Kung wala kang error at ang steady state value mo is 1. Okay. Yung error na negative 1 would make the output 2. Okay, kasi dadagdag siya. So yung take note na E equals R minus C. So kung negative to, okay. Kung if we compute for the output, this becomes R minus E. So, kung negative yung error mo, that means that becomes R plus E. Kung negative yung error ha. Okay, so that means yung input mo, halimbawa 1, tapos yung error mo na negative 1 should become 1 minus negative 1. Okay, so magiging 2 siya. So, a negative error means tumataas yung mas mataas yung signal mo dun sa dapat na settling value niya or final value niya. Okay, so ibig sabihin ito, yung negative 1 over 1,000 na to, it means mas mataas ito dun sa Okay. Now, if we actually assume na yung R of S nyo is also step signal, okay, take note na itong system niyo is a type 1 system. Okay, kung wala kasing DS, we can reduce this forward transfer function as 1,000 over S times S plus 25. So, this is a type 1 system. Okay. Type 1 system ito. And if this is a type 1 system, it would mean na 0 ang error nito sa step signal o sa step input o step RS. Okay? So, assuming that, ibig sabihin nun, kapag ka ang input natin ay step signal, tapos ang output natin, ang disturbance natin is a step signal, ang error lang ninyo, okay, would actually come from the, walang input galing sa, walang error galing sa input. Okay? Pero meron kayong error galing sa disturbance niyo. Okay? So in that case, pag ginawa natin, is-simulate natin ito, okay, that should be evident kagad. Kasi nga, 0 naman yung error nito. Ang makikita na natin ng error is itong negative 1/1000 na to. So, ang expected output natin actually dito, expected final value nung ano natin, nung output nung C of infinity natin, yung expected na value ng C of infinity is basically 1 kasi ito yung final value ng signal ninyo plus 0.001 or 1.001. Ito yung expected output natin or expected final value ng output natin. Okay? So, be-verify natin yan using the simulation. And this time, this is the first time na gagamitin natin ito. I'll use Simulink. Okay? Aaralin natin kung paano gumamit ng Simulink sa simulation. Okay? In your laboratory. Okay? So, this would be one of the activities. Okay? So, if it is possible na makapag-download na kayo ng Simulink, idagdag nyo dun sa MATLAB trial ninyo, please do so. Okay. So, here, makikita natin na ang ginawa natin is that ito yung inyong controller. Okay, and then this is your plant. Okay. Tapos ang input nyo is a step signal. Ang output nyo is ang disturbance is also step signal. Okay. Both of them start at 1 second time. So ibig sabihin from 0 to 1 second, 0 ito. Tapos magsisimula lang yung step signal nyo at 1. Mag-open at 1 second instant. Okay. So pero pwede naman palitan yung settings later on. Hindi ko na lang siya binanggit dito. And then kapag nirun natin ito, okay, at tinignan natin yung output natin which is measured by our scope, we would have the following. Yeah, we would have the following output galing doon sa simulation niyo. Okay, so as you can see, underdamped yung system niyo. Okay, which peaks at this point. Okay, so nagpipeak yan sa 1.235. Okay, at the time ng 1.109. So ito yung peak time niya, bale. Ito yung peak time niya, ito yung peak value niya. So, ang ano nito is kung i-relate nyo to sa sa final steady state value, it should have been 23.5% percent overshoot. Okay, so but that's time response. Okay. So, pinag-uusapan natin steady state error. So, itong cursor 2 ninyo, okay, measures na yung value ng y ninyo. Okay, measures yung value ng y ninyo at that particular point is 1.001. Okay? So, again, pinapredict natin galing dito na ang magiging final value ng output niyo ay 1.001. Okay? Ito yung pinapredict natin magiging value niya. Okay? Again, 0 yung tinitingnan nating error galing sa RS. Tapos, yung manggagaling na error galing dun sa step disturbance niyo is basically negative 1 over 1,000. Okay. Now, alternatively, pwede naman nating instead of measuring the error in terms of the output, you can actually measure the error in terms of the error itself by actually placing a probe here or by probing this signal. Okay. So, gagawin natin, okay, since itong signal na to, is your E of S. Okay. So, yun yung E of S nyo. Ang gagawin natin is that ililipat natin yung scope natin dito. Okay, tapos ipoprobe natin siya. Ayan. Okay, tapos ito pa isang gawin natin. Let us set this yung final value niya sa 0. Essentially, making your input 0. So what we will have here is that you will have a system whose input is entirely D of S. Okay? Your input is entirely D of S. Okay? So as we expect, ang error ninyo, okay, this is your error. Error ninyo due to the step disturbance is basically negative 1 over 1,000. So yun yung tingnan natin ngayon. Okay? So i-run natin ito. So, na-run na natin siya by pressing this one. And clicking on the scope will display the following. Okay. So, again, taking note of na ito yung steady state value ng signal niyo or ng output niyo. Or in this case, this is now the error signal. Okay. Makikita natin dito na yung value niya, yung value ng y niya is negative 1.003. Or that translates to negative 0.001. Okay, as predicted nung formula natin. Okay? So, ayun. So, yung simulation natin actually agreed with our theoretical formula, yung analytic formula natin. Okay. So, ayun. So let us proceed now in working on example 6.11. Okay. So in this case, let us evaluate the steady state error component due to the step disturbance for the system. Okay. So in this case, let us have ED, okay, or the error due to the disturbance as again negative 1 over the limit of 1 over G2 as S approaches 0 plus the limit of G1 as S approaches 0. Okay, so separately evaluate natin siya. Let us evaluate the DC gain of G1 as S approaches 0. Okay, so this is simply the limit of 1,000, that is simply 1,000. Okay, again, that constant naman yung G1 ninyo, so that is basically 1,000. Okay, now for number 2, we will have the limit of G2 as S approaches 0. That's basically 2 over 4 or 1/2. Okay, pero ire-reciprocal kasi natin siya. Okay, so yung ED nyo ngayon, okay, becomes negative 1 over 2 plus 1,000. Okay, so ang nangyari dito is that tumaas itong tumaas yung value nung DC gain natin. Okay, dito tumaas yung value nung DC gain ng G2. Okay, so ayun, so we will have negative 1 over 1,002. Okay, so we find now that the error is negative 1.002. Okay, or computing that using a calculator, that should give us negative 9.98. Okay, times 10 raised to negative 4, or basically this is negative 0.998 times 10 raised to negative 3 in terms of engineering notation. Okay, so kanina I was thinking to actually compare this to this one. Okay, kaya lang naisip ko pala the comparison is not correct. Okay, basically because they possess different values for your plant. Okay, so ayun. So anyway, this resulted to an error of negative 0.998 times 10 raised to negative 3. Okay. So we then simulate yung ating system to be able to determine yung error natin. Okay. So again, ito yung plant ninyo. This is your controller. Okay. And then we measure the error here. So after executing the system, okay, we will have the following waveform or output response plot para sa sa error signal niyo. So yung error signal niyo measures negative 9.981, okay, times 10 raised to negative 4, or basically yung almost similar dun sa nakuha natin. Okay, so yung nakuha natin from your calculation is negative in terms of negative 9.980, tapos ito negative 9.981. So may konting difference lang. Okay, pero still we were able to verify yung results nung nung ating analytic solution, okay, using yung formula natin from the theory at saka yung simulation natin using Simulink.